plus minus, good and evil. And we have a light side and a dark side of C++. And well, I don't know, there are people who think that doesn't mean it's a better language. And one of them is Felix von Leitner, who has made a case against C++. Please give him an applause.
Thank you. Okay, so I should start up with, my day job is auditing source code. So if I can, I audit source code. If I cannot, I audit binaries. And so I've seen C++ code from both points. And I'm trying to, so the main point I'm trying to make is that people usually focus on how easy it is to program in a language. And that shouldn't be the focus. The focus should be how easy it is to reuse code, to read other people's code, and to create good code in the first place. So I have three central complaints in this talk. The first one is that C++ creates new bug classes, but these are usually well known, so I move that to the back. C++ is hard to write and it's hard to read, and the last one is the big one. So as a warm-up, I Googled for C++ error messages, and I don't know actually what code does this, so I thought I should try myself to have one really typical C++ code. So this looks easy, and it should be easy. So the error is that I'm passing the wrong iterator type here. This is like a C++ 101 error. Should be really easy to fix once you see the error message, but the error message is not so easy. And that's the main problem. That's one of the main problems with C++. The language is so powerful that you can do lots of stuff with it, but you wouldn't do it directly in the language, but they implement the stuff in the language. And if you ever try to read STL code, you know what I'm talking about. So I'll get to that later. So I learned C++ a long time ago. There was no STL yet. And I learned it coming from C and having some exposure to what's now called Delphi. So I wanted to have object-oriented programming, and I wanted the inline functions, and I liked the idea of operator overloading and templates. So these are like the points I was opting for when I went to C++, and I wrote this commercial application back then in 1997. That was my biggest C++ project at that time. So it was a search engine, and I wrote it, it worked, it wasn't that big, but over the years I had to touch it a couple of times, and that's something that I find deeply disturbing. If the language has to be changed and you have to go over all your code and change the code. So these are not big changes, but the first one is can be annoying. So the lifetime of the declaration of I changed. And this looks obvious, like if you forget to change it, you get an error message, but some people use I more than once in different layers in the same code. So they declare a small instance of this, and I did this a couple times because I is usually my iterator in loops, like most people do. So you get really subtle errors just because the behavior of the language changed on me, and I had to go over all the code and change everything. And this is like wasted time. Right? This has happened a couple times with C++. These are the occasions that I remember, and that was the beginning of me not liking C++. So that's why I'm listing this. None of these is really that big of an issue, but if you have this old code and you wrote it once and you don't want to touch it, I mean that's usually the goal of code, that you write it once and then it works, and then you never have to touch it again. But eventually someone runs it on this Debian system and get update, and the libraries change, and so they recompile, and then it blows up. And this stuff is not necessary, and it caused lots of trouble for me, and that's why basically this happened. And the ever-changing styles is not just stuff you have to change, but also stuff that the best practices tell you to change. So how many people in this audience know why these changes are recommended by some people these days? It's actually quite obvious if you do C++, but so if you have an iterator, or I is not actually an int, but it's some class, then this one is a copy constructor. And so it can create a temp copy of the variable and then assign it, which usually doesn't matter these days because the code that being generated is the same. But if you changed this code to use iterators at one point and not an int, then maybe there is no smaller than operator for the iterator. Maybe it's just an iterator that you can advance and you can see if it's the last one. So usually for iterators you do this check. But this is all just best practices stuff. So some people don't just change the code because the language changes, but also because their idea of the language changes. And that means that in a usual grown C++ project you find all kinds of styles mixed together, and sometimes people just change things, and you need to look more than once to see what the code is doing, because maybe it's a different style you're not used to, and the language shouldn't be so powerful that you can do it in like a trillion ways, because then it makes reading harder. I mean, if any one of you is doing Perl, then you know what I'm talking about. So C++ is really optimizing in the wrong direction. It's not trying to be a language that you can write big projects in, but it's trying to be a language that if someone wrote this great library, then it's really easy to use the library. So STL is a library that by all standards is really good C++ code, and Boost is also very well known, and it's also very easy to use once you know it. But if you try to write a library that's that easy to use, then that's a whole snake pit of problems, and I'm trying to pinpoint a few of them. But one of the things I'm trying to say today is that even if you are a perfect C++ programmer, there's still problems for people who want to read the code. Even if you do everything right, then the auditor still has to look at lots of context suddenly that should be necessary. So writing a good library is almost impossible. I have a few examples of stuff that gets blown up in most cases, and reading a good library is even harder. So if you try to read the Boost code, I have some examples later for particularly bad stuff where if you look at it, you're not even sure how they did it. So, but this stuff like that can be done in C++. So the thing that I'm saying is that you should optimize to make the code readable. So that the easier it is to read the code, the easier it is to modify the code. And most people think I write this now and I never have to look at it again, but that's not how it happens. Even if it's not you, which is like even more often the case, particularly in the open source world, when you write some code and some other guy wants to port it somewhere maybe, or just wants it to compile with a different compiler version, or maybe the language changed, so he has to read the code to understand what the code does, and that's really much more difficult in C++ than it has to be. Usually code is written only once, and I'm not meaning that of course you throw away code and rewrite stuff, but if you look at every letter in the C++ program, then it was written once, but it is being read all the time by lots of people. So you should really try to write code that's easy to read and not easy to write. If you have to choose. If you don't have to choose, do both, obviously, right? So when I looked at how C++ works, I saw that it's easy. It's hard to parse, and not just for humans. So a human looks at this and sees the hooray and says, well, this should not compile, right? But if you look closer, then you see this is a template instantiation, and it declares this operator returns a pointer to this type T. But what this code tries to do is dereferences and want a reference. So the compiler sees this and goes here, and okay, it's no reference, so it reapplies this operator, and it's still no reference. It's one more pointer on top of it. So this is basically an easy endless loop, and because it's you wouldn't believe it if you have never seen it. I put it in this code, and you see this is actually not even the compiler, this is just the parser that's hanging. And you can watch it consume ever more memory, trying to go through this hierarchy of types. And you know, if the compiler can't read the code, then how can you expect people to read the code, right? So this looks worse than it is. What this code basically does, it has two structs and both define the same type. So there's a type def inside the struct for foo, data type foo. Then it declares two structs that both inherit from this class. So both now have a type foo. And if you do a multiple inheritance on these two classes now, then the compiler has to check that in all branches, foo is a compatible type. So what this code does, I'm using the preprocessor so it fits in on the slide, but what this code basically does, it does multiple inheritance recursively. So in the end, you have like this tree of structs all doing multiple inheritance, basically in the end on this A, but you have 2 to the power of, I think, 10 or something in the end of subclasses, all with a type foo. And if you used to put this in G++, then it consumes like a gig of memory. And the algorithm to do this type checking was n to the power of 4. And it took like an hour to run on a decent machine. And so they fixed it in G++, but the Intel compiler, for example, still just hangs and consumes CPU. And you could just, I aborted after 90 minutes on this Core 2 Duo notebook. So this is not just academic. This is, I mean, this code is small enough that you could understand it if you spend some time on it, right? And this is even in C++, the parser becomes more and more big in the context it needs to consider. So this is maybe hard to swallow, but you can cut and paste it. I'll publish the slides later. So actually, I think I have it. Yeah. Okay, so let's just let it run and we can come back later. So one of the things in C++ is that even if you try to use everything right, the compiler still needs more context than it used to be. In C, you have Elexir that just parses this double quotes and says this is a double quotes token, for example. And then you have a parser that builds a parse tree, and then you have the next step that works on the parse tree. But in C++, the part that builds the parse tree has to know about types and has to build the symbol table. So it's all moved together in one part. And we saw already in the other example how you can create loops in this. But even there are some subtle inconsistencies that people just, you may call it warts in the language. But you see, if you see this, and it's perfectly obvious to me at least, that if you don't give it a string, then it should still do the same basic thing, right? But it doesn't. It declares a local function. And this is a newbie error. There's a C++ FAQ, and it lists lots of things like these. So if you have like a couple days time, you should look at the FAQ. It's really enlightening. So other examples are that when the code looks the same, but in some other place you changed something, then suddenly the meaning of the code changes. So in C and C++, you have certain guarantees on where the compiler is allowed to rearrange the order in which stuff is executed, or if it's even executed at all. For example, for this Boolean AND operator, the standard says that if A is not true, then you don't have to check this, right? Because the combined can never be true. So this is also true in C++, except if someone overloads the operator. Then both sides are evaluated. And so if you have a statement that uses this, then you used to be able to just say, okay, so the second part is probably not executed, or maybe, but in C++ you have to look if there's an operator overloading here. So even if the code looks the same, it does something different suddenly. And even I have this example which I find pretty neat about how the parse tree changes depending on context you didn't need earlier on. So this, if foo is a type, then this is a typecast, and this is the unary plus operator, which doesn't do anything, and so this is calculated and then cast to foo, right? Actually, the A is cast to foo, and the multiplication is on the foo. But maybe foo is not a type, then that's how most people read it anyway. Then it's a plus of foo and this product, right? So the statement looks the same, but suddenly, using context you didn't need earlier, suddenly the meaning changes. And even the parse tree changes. So if you learn compiler design or compiler writing on the university, then this didn't occur in the textbooks, because in most languages this type of construct doesn't exist. So it's really hard to write a C++ compiler, and you can see that on most compilers on the market. It took them like 20 years to iron out most of the problems. And they're still really slow compared to C. So just so you know, it's still going, right? So the similar thing to the end operator is the comma operator, which is kind of obscure, so but I'm still listing it. So in C and C++, if you have A, comma B, then it means A is evaluated and then B is evaluated. But if someone declared a different operator, then suddenly the meaning changes, and it could be that this doesn't matter in the normal case, but this could be a function call that modifies some data structure somewhere completely else, right? So suddenly you need to look at both and figure out the order.